Paper one.
Hello, so this is group one, and we chose to do the earthquake data sets for this project. We essentially uploaded the CSV earthquakes into IBM Cognos Analytics. And as for the fields we utilize, we use the magnitude, significance, depth, distance, gap, location, time, and year. The data set has earthquakes from all around the world, from the dates July 27, 2016 to August 25th, 2016. And within this time period, there were 8,394 earthquakes recorded.
This slide shows the number of earthquakes per country. The count ranges from 1 to 3,609. California has the highest number of earthquakes recorded, and this shows that Alaska is second and Nevada is in third. Countries with lower number of recorded earthquakes are harder to differentiate, so this graph really communicates how these three areas have a higher frequency of earthquakes than the rest of the world. This slide describes the magnitude for the data set. At the top, we see that the average magnitude recorded reached 1.51. Below, we see a column graph for all earthquakes. The most frequent section of the earthquakes were in the 1.09 to 1.24 range, with a total of 778 earthquakes. Not far behind it was 0.78 to 0.93 magnitude, with a total of 769 total earthquakes. Slide 5 shows the magnitude and significance for the dataset. On the left, magnitude is charted in blue and significance is in the green dots. This is graphed by days. Throughout the days, there seems to be no trend, and so it is difficult to gain insight over such a short time period, as this dataset only occurs for 1 month. On July 20th, the highest significance sum was 2,405, and on August 1st, the highest maximum peak of magnitude was at 541.14. On the right, we see a correlation between magnitude and significance. It shows a strong positive correlation between these two variables. So this means that as the magnitude of the earthquake increases, the significance from the earthquake also increases. This can be attributed to the increase in seismic activity and the increase in causing more damage. This slide here shows a side-by-side comparisons of earthquake magnitudes in Alaska and California. On the left, Alaska shows a large spike in magnitudes between 1.09 and 1.2 for a total of 291 earthquakes in this range. Opposingly, California takes on a more skewed bell-shaped curve. There is no one single peak, and the range of 38% of magnitudes fall under a larger range from 0.52 to 1.03. This shows that many earthquakes in California did not reach a level 1 magnitude, but in Alaska, the majority of earthquakes are all at a level 1 reading. Slide 7 shows individual earthquakes by magnitude and at their longitudinal and latitudinal points. When earthquakes occur in the same exact coordinates, an average in magnitudes are presented. The range in these magnitudes range from 0.01 to 7.7. Again, we hone in on the magnitude for Alaska as well as the continental US. On the left, we see earthquakes in many states as well as off the coast of Oregon. A large cluster of earthquakes occur along the Pacific West Coast as well as the central US and around Oklahoma and Kansas specifically. The ranges for these magnitudes are from 0.01 to 5.09. Then on the right, we see Alaska earthquakes. These earthquakes range from 0.1 to 5.6, so slightly stronger than those in the continental US. A large majority of these earthquakes fall along Alaska's southern island chains. There is a strong correlation with geography and location of the earthquake, as it shows the majority fall along the same curve.
In this figure, the decision tree shows the predicted significance of an earthquake. The first rule is a decision between various locations such as California, Nevada, Puerto Rico, and others. Since the magnitude is correlated with significance, as early stated, as the magnitude is bigger, the significance will also be greater. In the next figure, the decision tree is for predicting magnitude. The rules for this figure shows various significance level, and again, as the significance is higher, the magnitude is greater. It also shows a decision that corresponds to a couple of locations based on the impact of the earthquake. For the next figure, shows a driver analysis where it takes multiple drivers and predicts the strength of magnitude. From analysis of the dataset, we found that the field's distance, depth, gap, and significance heavily influence magnitude size. So when at least 3 drivers are combined in the driver analysis, there is at least a 92% predictive strength of magnitude. If we look at this figure, it shows the calculation of distance, depth, gap, and significance, which is denoted as top driver variable. And once that is paired with their respective magnitude, there is clearly a correlation. As the average of the top driver variable increases, so does the magnitude, which backs the findings and insights in the driver analysis. And finally, this boosted for magnitude figure shows the calculations of the previous top driver, which is again distance, depth, gap, and significance multiplied by the current magnitude, which produces the field boosted. And as expected, the boosted sum increases as the magnitude increases.
Based on our analysis and visualizations, these answer the questions that are stated in our written document. And so that concludes our analysis of the earthquakes dataset.